Something is wrong with the universe. Not wrong in a poetic sense, not wrong as a figure of speech, wrong in the precise, measurable, reproducible sense that makes physicists uncomfortable. The kind of wrong that keeps entire research groups awake, that generates hundreds of papers per year, that Nobel Prize winners describe in public lectures with language they would not have used a decade ago. In 2019, Adam Rees, one of the scientists who discovered that the expansion of the universe is accelerating, work that earned him the Nobel Prize in Physics, used a specific phrase in describing the discrepancy at the center of modern cosmology. He said, "The numbers are in tension at a level that suggests it's not a statistical fluctuation, it's not a systematic error. It might be telling us something about the universe that we didn't know." That discrepancy is called the Hubble tension, and James Webb Space Telescope has made it worse. Not better, worse. The expectation when Webb launched in December 2021 was that its extraordinary precision, its ability to observe individual stars and galaxies with a clarity and depth no previous telescope had achieved, would resolve the Hubble tension. That Webb would look at the same objects previous telescopes had used to measure the expansion rate of the universe and find that the discrepancy was an instrumental error, a calibration issue, something that could be corrected and made to go away. Webb has been operating for over 2 years. The data are in. The measurements have been made with Webb's superior resolution and sensitivity. The discrepancy has not gone away. If anything, it has sharpened. Tonight, we are going to follow this story carefully, from the basic physics of measuring the expanding universe, through the specific discrepancy that is dividing cosmology, through what Webb has found and what it means, to the possibility that we are looking at something genuinely new. Something that is not in our current theory of the universe. Something that our best physical model, the model that has passed every previous test for decades, may not be able to accommodate without fundamental revision. This is not speculation. This is the current state of observational cosmology. The tension is real. The measurements are reproducible. The Nobel laureates are concerned. If the night is long, stay. This is a story about the possibility that we are living through one of those rare moments in science where the instruments get good enough to reveal that the map is not the territory. Where data accumulated carefully over years forces us to confront that something we thought we understood, something we thought we had measured, is not what we thought it was. Let us start at the beginning. The universe is expanding. This has been known since 1929, when Edwin Hubble published his measurements showing that galaxies are moving away from us and that more distant galaxies are moving away faster. The velocity at which a galaxy recedes is proportional to its distance. The proportionality constant is called the Hubble constant, h0, and it tells us the current rate of expansion of the universe. In Hubble's original measurement, the value was approximately 500 kilometers per second per megaparsec. This means that a galaxy 1 megaparsec away, about 3.26 million light-years, moves away from us at 500 kilometers per second. A galaxy 2 megaparsecs away moves at 1,000 kilometers per second, and so on. Hubble's original value was badly wrong, by nearly an order of magnitude. The problem was that the distance scale was not yet calibrated correctly. In the decades following Hubble's original measurement, astronomers worked to establish a reliable distance ladder, a chain of measurement techniques each calibrated against the next, extending from nearby objects to the most distant galaxies. The distance ladder is the central concept here. We cannot measure the distance to a galaxy directly the way we can measure the distance to a nearby tree with a tape measure. Galaxies are too far away. Instead, we use a chain of overlapping techniques. The first rung parallax. For stars within a few thousand light-years of Earth, we can measure their apparent shift in position as Earth moves around the Sun. This apparent shift, the parallax angle, is directly related to distance through simple trigonometry. The European Gaia satellite has measured parallax distances to billions of stars with extraordinary precision. The second rung, Cepheid variable stars. Cepheids are a class of pulsating stars that vary in brightness with a period that is directly related to their intrinsic luminosity. By measuring the period of a Cepheid, you know its true brightness. By comparing this to its apparent brightness, you can calculate its distance. Cepheids are visible in nearby galaxies, a bridge from the local stellar neighborhood to the wider universe. The third rung, Type 1a supernovae. When certain white dwarf stars in binary systems accumulate enough mass from a companion star, they explode as supernovae. These explosions, Type 1a supernovae, all reach approximately the same peak intrinsic brightness. They are extraordinarily luminous, visible across billions of light years. By measuring how bright a Type 1a supernova appears, and comparing to how bright it actually is, you can calculate the distance to the galaxy it occurred in. This distance ladder, parallax to Cepheids to Type 1a supernovae, is the primary tool for measuring H0 from observations of the nearby universe. And here is where the tension begins. When astronomers use this distance ladder to measure H0, they consistently get a value of approximately 73 kilometers per second per megaparsec. The most precise measurement comes from the SH0-ES collaboration, supernovae H0 for the equation of state, led by Adam Rees. Their latest value is approximately 73.04 plus or minus 1.04 kilometers per second per megaparsec. But there is another way to measure H0. Instead of measuring the expansion of the nearby universe directly, you can use the early universe, specifically the pattern of fluctuations in the cosmic microwave background radiation. The cosmic microwave background, CMB, is the thermal radiation left over from when the universe was about 380,000 years old, when it cooled enough for electrons and protons to combine into neutral hydrogen and the universe became transparent. The CMB pervades the entire universe at a temperature of about 2.725 Kelvin and contains tiny fluctuations, temperature variations of about 1 part in 100,000, that encode information about the conditions in the early universe. The pattern of these fluctuations, specifically the angular scale of the acoustic peaks, the characteristic sizes of hot and cold spots, depends on the physical conditions of the early universe, including the expansion rate at that time. If you know the physical processes that created the CMB fluctuations, and you measure their angular scale precisely, you can infer what H0 must be today for the universe to have evolved from those initial conditions to what we observe. This is what the Planck satellite did. Planck measured the CMB with extraordinary precision from 2009 to 2013. From the CMB data, using the standard cosmological model called lambda CDM for cosmological constant and cold dark matter, the inferred value of H0 is approximately 67.4 plus or minus 0.5 kilometers per second per megaparsec. 73 versus 67. These two numbers, from two completely different methods of measuring the same physical quantity, disagree by about 8%. And the statistical significance of this disagreement has grown as both measurements have improved. Early measurements of this discrepancy were at the 2 to 3 sigma level, possibly a statistical fluctuation. Current measurements are at approximately 5 sigma. In physics, 5 sigma is the threshold for claiming a discovery. A 5 sigma discrepancy between two measurements of the same quantity is not a statistical fluctuation. something is genuinely wrong. Either the distance ladder has a systematic error, or the CMB analysis has a systematic error. Or the standard cosmological model is wrong, incomplete, or simply incorrect in some fundamental way. Before Webb, the most common explanation offered by skeptics of the tension was that the Cepheid measurements had a systematic error. Cepheids are not simple objects. They exist in crowded stellar environments. Their light can be blended with light from nearby stars. The calibration of the Cepheid period luminosity relationship depends on observations of Cepheids in the Large Magellanic Cloud and other nearby galaxies. Any systematic error in how Cepheids are identified and measured could propagate through the entire distance ladder and shift the inferred value of H0. This was a reasonable concern. It was testable, and Webb was the instrument to test it. Webb was designed for exactly this kind of measurement. Its infrared sensitivity, Cepheids in crowded galactic environments are much cleaner to observe in the infrared than in optical wavelengths, because dust absorbs optical light but is largely transparent to infrared. And its extraordinary spatial resolution, allowing individual stars to be separated in distant galaxies, made it the ideal instrument to check the Hubble Space Telescope's Cepheid measurements independently. The SHOES team used Webb to observe Cepheids in the host galaxies of Type 1a supernovae, the same galaxies they had used with Hubble Space Telescope. With Webb's superior resolution and infrared capability, they could check whether the Hubble measurements of these Cepheids were affected by crowding, by contamination from nearby stars that Hubble could not resolve. The results, published in 2023, were unambiguous. The Webb measurements of the Cepheids agreed with the Hubble measurements to within the measurement uncertainties. There was no significant crowding bias. The Cepheids Hubble measured were not contaminated by nearby stars at a level sufficient to explain the Hubble tension. Adam Rees, presenting these results, was direct. The systematic error that critics had proposed, the one that would explain away the tension, was not there. The distance ladder measurements were robust. The Hubble tension was real, at a level of approximately 5 sigma. With the most precise instrument ever built for this kind of measurement, having confirmed the distance ladder rather than revealed an error in it, something is genuinely wrong. Let us talk about what it means for something to be wrong in cosmology, what the actual options are for resolving a 5 sigma discrepancy between two measurements of the same physical constant. The first option is measurement error. Despite Webb's confirmation of the distance ladder, this is not entirely excluded. The error could be in the CMB analysis rather than in the local measurements. The Planck satellite's measurement of the CMB is extraordinarily precise, but the inference of H0 from the CMB data depends on assuming the standard cosmological model. If the model is wrong, the inferred H0 from the CMB would be wrong, even if the CMB measurement itself is perfectly accurate. The second option is unknown systematic error in the distance ladder. Even with Webb's confirmation, there could be systematic effects that affect both Hubble and Webb in the same way. If something in the fundamental calibration of Cepheids is wrong, something that affects all optical and infrared observations of Cepheids in the same direction, it would not be caught by comparing Webb to Hubble. The third option, and the one that cosmologists are increasingly being forced to take seriously, is that the standard cosmological model is incomplete or wrong, that there is new physics operating in the universe that our model does not account for, that the universe is doing something in the 13.8 billion years between the CMB epoch and today that our equations do not capture. This third option is what Nobel Prize winners mean when they say we might be seeing a different universe. Not literally a different universe, but a universe whose behavior is not fully captured by our current best model. The same model that successfully predicted the CMB fluctuations, the large-scale structure of the galaxy distribution, the abundances of light elements, and dozens of other cosmological observables. Let us talk about what James Webb has been finding beyond the Hubble tension, because it is not just the expansion rate that is surprising. Webb was designed to see farther and more clearly than any previous telescope. It observes primarily in the infrared, which allows it to see light that has been redshifted, stretched to longer wavelengths, by the expansion of the universe from the most distant and therefore earliest galaxies. Webb was expected to find the first galaxies, objects from the first few 100 million years after the Big Bang, and to characterize their properties. What it found was unexpected. Within its first year of operation, Webb identified numerous galaxy candidates at extraordinarily high redshifts, corresponding to epochs when the universe was only a few 100 million years old. This was expected. What was not expected was how massive, how bright, how structurally developed these early galaxies appear to be. The standard model of cosmology and galaxy formation predicts that the earliest galaxies should be small, irregular, actively forming stars from primordial gas for the first time. The universe at 300 million years old should contain mostly tiny, chaotic proto-galaxies, the seeds from which later large galaxies like the Milky Way would grow through billions of years of mergers and accretion. Some of the galaxies Webb found in the early universe are not like this. Some appear to be surprisingly massive, containing stellar masses comparable to galaxies in the local universe that took billions of years to assemble. Some appear to have already stopped forming stars, quenched their star formation, at a time when the universe was barely 700 million years old. Some show organized disk structures, the flattened, rotationally supported structures we associate with mature spiral galaxies, at redshifts where no models predicted them. One particularly striking example. In 2022, Webb identified a set of galaxy candidates at redshifts corresponding to the universe being only about 300 to 500 million years old. Some of these candidates, later confirmed spectroscopically, have stellar masses suggesting they formed billions of solar masses of stars in a very short period immediately after the Big Bang. In the standard model, this is difficult to account for. The rate at which gas can cool and collapse into stars is limited by physics. The rate at which dark matter halos, the gravitational scaffolding within which galaxies form, can grow is limited by the expansion rate of the universe. Early enough in cosmic history, there should simply not have been enough time for such massive structures to form. The early universe seen by Webb contains more massive, more evolved, more organized galaxies than the standard model predicts. Is this a crisis for the standard model? That word is being used with increasing frequency in the cosmological literature. Not yet a definitive crisis, the observational uncertainties are still significant for the highest redshift objects. Photometric redshifts can be wrong, stellar mass estimates depend on model assumptions. But the trend is consistent and growing. With each passing semester of Webb observations, more high redshift massive galaxies are confirmed. The discrepancy between what the standard model predicts and what Webb finds in the early universe is not going away as the data improve. It is accumulating. Поговорим о конкретном объекте, который потряс больше всего, о так называемых больших маленьких галактиках ранней Вселенной. В 2023 году команды, использующие данные Уэбба, опубликовали результаты, описывающие ранние галактики, которые не только массивны, но и компактны. Они содержат столько же звездной массы, сколько крупные современные галактики, но занимают значительно меньший объем. Это само по себе не является шокирующим. Было известно, что ранние галактики в среднем компактнее, но Уэбб показал, что некоторые из этих компактных массивных ранних галактик уже имеют регулярные морфологии, форму, которую вы бы ожидали от зрелых устойчивых систем, а не от хаотичных молодых галактик. Они выглядят как миниатюрные версии современных эллиптических и дисковых галактик, уже структурно организованные в то время, когда Вселенная еще не достигла 1 миллиарда лет от роду. Модели образования галактик в рамках стандартной космологии предсказывают, что галактики растут через слияние и аккрецию, постепенно объединяясь и обретая структуру на протяжении миллиардов лет. Видеть хорошо организованные, массивные, структурно зрелые системы уже на от 500 до 700 миллионов лет не противоречит стандартной модели в абсолютном смысле, но это значительно нагружает ее возможности. Некоторые из этих ранних галактик также показывают признаки уже содержащих сверхмассивные черные дыры в своих центрах. Черные дыры с миллиардами солнечных масс, уже существующие, когда Вселенная была еще молодой. Стандартные модели роста черных дыр через аккрецию и слияние с трудом производят такие объекты за такое короткое время. Let us talk about what specifically makes these early massive black holes so difficult to explain, because this is one of the sharpest confrontations between Webb's observations and our standard theoretical picture. In the standard model of black hole growth, supermassive black holes build their mass through accretion, consuming gas that falls into them, and through mergers with other black holes. Both processes take time. There are physical limits on how quickly a black hole can accrete, the Eddington limit, which is set by the balance between the outward radiation pressure from infalling gas and the inward gravitational pull. A black hole accreting at the Eddington limit doubles its mass in roughly 45 million years, an Eddington timescale. Starting from a black hole seed, the remnant of the first massive stars, perhaps 100 to 1,000 solar masses, and growing at the Eddington rate continuously, you need roughly 1 billion years to reach a mass of 1 billion solar masses. But Webb is finding black holes with masses of hundreds of millions to billions of solar masses, when the universe is only 500 to 700 million years old. There is not enough time for standard Eddington rate accretion starting from ordinary stellar remnant seeds. Several solutions have been proposed. Super Eddington accretion. If black holes can accrete faster than the Eddington limit allows under certain conditions, could speed up mass growth. Direct collapse black holes. A theoretical model in which certain regions of pristine primordial gas collapse directly to black holes of tens of thousands of solar masses, bypassing the normal stellar evolution pathway, would provide heavier seeds that need less time to grow. Primordial black holes. Hypothetical black holes formed in the early universe before any stars existed, could also serve as heavy seeds. Each of these proposals addresses the problem, but introduces its own complications. Super Eddington accretion requires specific physical conditions and is not well understood theoretically. Direct collapse black holes require pristine metal-free gas in very specific conditions that may be rare. Primordial black holes require physics beyond the standard model to be produced in the required abundance. The fact that multiple exotic solutions are being invoked to explain what Webb is seeing, each requiring special conditions or new physics, is itself a sign that the standard model is struggling. What Webb has revealed is not that supermassive black holes exist in the early universe. We knew that from quasar observations going back decades. Webb has revealed that they appear to be more common, more massive, and present at earlier times than our standard models of black hole formation and growth comfortably accommodate. This is a quantitative problem, not a qualitative one. Supermassive black holes in the early universe are not forbidden by the standard model. They are just harder to make than the standard model suggests, in less time than the standard model provides. Let us talk about what the Hubble tension and the early universe anomalies might have in common, because there is a possibility that they are symptoms of the same underlying issue rather than separate problems. The Hubble tension is a discrepancy between the expansion rate measured locally from the distance ladder and the expansion rate inferred from the early universe CMB. One way to read this discrepancy is that the universe expanded faster in its early history than the Standard Model predicts, which would make it effectively older in terms of how much structure had time to form by any given epoch. If the universe expanded faster in its early history than we think, if there was some additional energy component or some modification to gravity at early times that boosted the expansion, then there would have been more time for early galaxies to form, more time for early black holes to grow, more time for structures to organize themselves before the epoch when Webb is observing them. This is speculative. The proposed modifications to the Standard Model that could resolve the Hubble tension, early dark energy, modified gravity, new relativistic species, phase transitions in the early universe, are many and varied, and most of them have not yet been shown to simultaneously explain both the Hubble tension and the early galaxy anomalies. But the conceptual connection is interesting. If something in the early universe is different from what the Standard Model assumes, if the expansion history between the CMB epoch and today is not what lambda CDM predicts, then both the locally measured expansion rate today and the properties of early galaxies could be affected. Some theorists have proposed that both the Hubble tension and the early galaxy anomalies point to a universe that is slightly older than the Standard Model predicts, that the standard age of 13.8 billion years may be an underestimate. If the universe is somewhat older, there is more time for early galaxies and early black holes to form, and the locally measured expansion rate would be consistent with a different expansion history. This is a minority view. The standard cosmological model is constrained by many independent measurements, and simply making the universe older does not resolve all tensions simultaneously. But it illustrates the kind of thinking being done in the theoretical community in response to Webb's observations. Let us talk about a specific observation from Webb that has attracted particular attention: the discovery of what have been called little red dots. In 2023 and 2024, as Webb has accumulated data on high redshift galaxy fields, a population of objects has emerged that was not predicted. Compact red sources at high redshifts, appearing in numbers significantly exceeding what standard models predict. These objects, dubbed little red dots informally in the community, appear to be a mixed population. Some are likely very compact, dusty, starburst galaxies, galaxies forming stars at prodigious rates, with the starlight reddened by dust. Some appear to be active galactic nuclei, growing supermassive black holes that are more common at early times than expected. Some may be a combination of both. The abundance of little red dots, how many of them Webb finds per unit volume of the early universe, exceeds predictions. Models based on the known distribution of galaxy properties and the expected rate of black hole growth in the standard cosmological framework do not produce as many of these objects as Webb observes. This overabundance is another data point in the growing picture that the early universe contains more active structure, more star formation, more black hole growth, more organized galactic activity than the Standard Model predicts. The little red dots are particularly interesting because they appear at redshifts of approximately 4 to 8, the universe at 1 to 1.5 billion years old, in a regime where previous telescopes had some coverage and where our theoretical models are more constrained than at the very highest redshifts. This is not the regime of the very first galaxies, where observational uncertainties are largest. It is a regime where discrepancies between models and observations are harder to attribute to measurement uncertainty. Let us talk about one specific Webb result that had particular resonance with the broader astronomical community: the spectroscopic confirmation of extremely high redshift galaxies that were initially found as photometric candidates. When Webb first released data in 2022, several teams independently identified galaxy candidates at redshifts of 10, 12, even 16, the universe at 200 to 400 million years old. Some of these candidates had photometric redshift estimates suggesting stellar masses that seemed implausibly large. Photometric redshifts are estimated from the colors of a galaxy, from how its light is distributed across different wavelength bands. They are useful but uncertain. A galaxy can be misidentified as being at a very high redshift when it is actually much closer, if its colors happen to mimic those of a high redshift galaxy. The critical step was spectroscopic confirmation, obtaining actual spectra of these objects, measuring the wavelengths of specific emission or absorption lines whose intrinsic wavelengths are known, and thereby measuring the redshift directly and unambiguously. Webb has now spectroscopically confirmed numerous galaxies at redshifts above 10. The highest confirmed spectroscopic redshift as of 2024 is approximately 14.3. A galaxy called JADES-GS-Z14-0, corresponding to the universe at about 290 million years after the Big Bang. This galaxy is not a faint smudge. It is bright enough that Webb can detect its light clearly. It shows emission lines, evidence of ionized gas, star formation, chemical enrichment. Its properties, estimated stellar mass in the hundreds of millions of solar masses, are substantial for an object seen when the universe was barely 300 million years old. This is an observational fact now, not a photometric candidate. A spectroscopically confirmed galaxy with directly measured redshift, seen when the universe was 2% of its current age. How did it get so massive so quickly? The standard model of structure formation, based on the growth of dark matter halos from tiny quantum fluctuations in the early universe, amplified by gravitational instability, predicts that the most massive objects form last from the progressive merging of smaller structures. The very largest halos at any epoch form at the upper tail of the mass distribution, and their formation rate depends on the expansion history of the universe and the primordial power spectrum of density fluctuations. JADES-GS-Z14-0 and objects like it are not impossible in the standard model. They could, in principle, be formed from extremely rare peaks in the primordial density field. But their apparent abundance, the fact that Webb keeps finding such objects rather than one exceptional case, is harder to explain as a tail of the distribution. If these objects were truly rare peaks, you would expect to find very few of them. Webb keeps finding more. With each new field observed, each new semester of data, the population of surprisingly massive early galaxies grows. The rarity argument becomes increasingly strained when you keep finding more examples. Let us now talk about what the phrase Hubble tension has evolved to mean in the current scientific discourse, because the conversation has moved significantly since the tension was first clearly identified around 2016 to 2019. In the early discussions, the Hubble tension was framed primarily as a measurement problem. The two values of h0 were in conflict, but neither measurement was definitive, and the most conservative interpretation was that one or both had unidentified systematic errors. This was reasonable. The history of measurement in cosmology is full of systematic errors that turned out to be subtle but important. The discussion today is different. Multiple independent measurements of H0 from the local universe, using Cepheids, tip of the red giant branch stars, gravitational lensing time delays, surface brightness fluctuations, type II supernovae, megamasers, consistently give values clustering around 72 to 74 kilometers per second per megaparsec. They use completely different physical phenomena, different galaxies, different calibrations. They agree with each other. Multiple measurements from the early universe and large-scale structure, from the CMB, from baryon acoustic oscillations, from the clustering of galaxies, consistently give values around 67 to 68 kilometers per second per megaparsec. They use completely different techniques from the local measurements and agree with each other. The tension is not between one local measurement and one early universe measurement. It is between two clusters of mutually consistent measurements that use entirely different physical phenomena and entirely different objects and entirely different calibrations. The local cluster says 73. The early universe cluster says 67, and they do not agree. This pattern, two internally consistent but mutually inconsistent clusters of measurements using completely different techniques, is much harder to attribute to a systematic error in any single measurement. A systematic error would have to affect all local measurements in the same direction without affecting any early universe measurements. Given the diversity of techniques in each cluster, this seems increasingly unlikely. This is what drives the growing seriousness of the theoretical response. The Hubble tension is looking less like a measurement problem and more like a physics problem. Let us talk about the specific theoretical proposals that have been made to resolve the Hubble tension, because the range of proposals is itself informative about the state of thinking in the field. The most studied proposal is early dark energy. In the Standard Model, dark energy, the mysterious component driving the current accelerated expansion of the universe, behaves like a cosmological constant, a fixed energy density of empty space that has been constant throughout the universe's history. Early dark energy proposes that there was an additional dark energy component active in the early universe, before the CMB epoch, that briefly boosted the expansion rate and then decayed away. This would reduce the physical size of the sound horizon at recombination, the scale imprinted on the CMB, requiring a higher H0 today to match the observed angular scale of the CMB peaks. Early dark energy can raise the CMB inferred H0 and partially close the tension. But it does so imperfectly and introduces new tensions with other cosmological observables, particularly with measurements of large-scale structure that constrain how clumpy the universe is. Early dark energy that raises H0 tends to also increase the predicted clumpiness of matter, which conflicts with weak gravitational lensing observations. Modified gravity is another category of proposals. General relativity, Einstein's theory of gravity that underlies all of standard cosmology, has passed every observational test on scales from millimeters in laboratory experiments to the scale of the solar system to the scale of individual galaxies and galaxy clusters. But it has not been tested on the scale of the observable universe in the way that lambda-CDM cosmology assumes it operates. Modifications to gravity on cosmological scales could change the expansion history without conflicting with local tests of gravity. Decaying dark matter. Proposals in which a component of dark matter decays into radiation at late times can also shift the expansion rate. So can models with new light species, additional particles beyond the Standard Model that contributed to the energy density of the early universe. So can models in which dark energy is not a constant but varies with time, dynamical dark energy. Each of these proposals has been worked out in varying degrees of theoretical detail. Each makes specific predictions for other observables. None has emerged as a clearly preferred solution that simultaneously resolves the Hubble tension and remains consistent with all other cosmological data. This is the honest state of the field. The problem is identified. The measurement is confirmed by Webb. The theoretical solution is unknown. Let us talk about a completely independent line of evidence that is bearing on the Hubble tension. Gravitational wave standard sirens. When two black holes or neutron stars merge, they emit gravitational waves that are detectable by LIGO and Virgo. The amplitude of these gravitational waves is directly related to the masses and distance of the merging objects. Unlike electromagnetic observations, the gravitational wave signal directly encodes the distance to the source without needing a calibrated distance ladder. This makes gravitational wave events, particularly those with electromagnetic counterparts that provide a redshift measurement, independent standard sirens for measuring H0. You measure the gravitational wave amplitude to get the distance, you measure the redshift of the host galaxy from its spectrum, and you get H0 directly. The first measurement of this kind came from GW170817, the neutron star merger in 2017, that was observed in both gravitational waves and across the electromagnetic spectrum. The H0 value from this single event was approximately 70 plus or minus 12 kilometers per second per megaparsec. With such large uncertainty, it was consistent with both 73 and 67, not yet discriminating. As more events accumulate and the uncertainty decreases, gravitational wave standard sirens will become an increasingly powerful test. Current estimates suggest that approximately 50 to 100 well-observed events with electromagnetic counterparts would be needed to reduce the uncertainty enough to definitively prefer one value over the other. We do not yet have 50 to 100 such events, but the program is underway, and as LIGO and Virgo continue to operate, and as the next generation of gravitational wave detectors, Einstein Telescope, Cosmic Explorer, come online, this independent measurement will become more precise. The importance of the gravitational wave approach is that it is entirely independent of both the local distance ladder and the early universe CMB analysis. It does not use Cepheids. It does not assume the standard cosmological model in deriving H0. If gravitational wave standard sirens consistently return a value close to 73, that would be very strong evidence for the local distance ladder. If they return a value close to 67, that would suggest something is wrong with the local measurements, despite Webb's confirmation. If they return a value in between, say 70, that would be, in some ways, the most uncomfortable outcome, suggesting that both the local and early universe measurements have systematic offsets in opposite directions, or that some new physics is at work that affects all measurements. We do not yet know which of these outcomes will occur. Let us talk about the S8 tension, a separate but related problem in cosmology that Webb's observations also bear on. S8 is a parameter describing the amplitude of matter fluctuations in the universe, essentially how lumpy or clumpy the distribution of matter is on certain scales. It is a combination of the matter density parameter and the standard deviation of matter fluctuations. Like H0, S8 can be measured in two ways: from the CMB, using Planck's measurements of the power spectrum of temperature fluctuations, you get a predicted value for S8 in the local universe. From direct observations of the local universe, using weak gravitational lensing surveys like KIDS, DES, and HSC, which measure how galaxy shapes are distorted by intervening matter, you get a measured value of S8. The CMB predicted S8 is higher than the locally measured S8. The universe appears to be slightly less clumpy today than the standard model predicts, based on the initial conditions measured in the CMB. This S8 tension is at approximately 2 to 3 sigma, less severe than the Hubble tension, but persistent across multiple independent surveys using different galaxy samples and different analysis techniques. What is interesting about the S8 tension in the context of Webb is that some of the proposed solutions to the Hubble tension, like early dark energy, tend to make the S8 tension worse. Early dark energy raises H0 toward the locally measured value, but also raises the predicted matter clustering, making S8 even more discrepant from the local measurements. This creates a situation where proposed solutions to one tension exacerbate another. The standard model has multiple tensions simultaneously, and fixing one tends to introduce or worsen another. This pattern, where modifications to the model are constrained from multiple directions simultaneously, suggests that any successful resolution will require something significantly different from a simple modification. It may require rethinking foundational assumptions. Let us talk about what this situation looks like from the perspective of a practicing cosmologist, what it actually means to be working in this field right now. Before the Planck CMB data of 2013 to 2015, cosmology had a problem in the other direction. The parameters of the standard model were uncertain enough that there was significant freedom in how to fit the data. Multiple models could accommodate the available observations. The Planck data constrained the standard cosmological model so precisely that most alternatives were ruled out. Lambda CDM became a highly predictive model. It made sharp predictions for the abundances of galaxy clusters, the matter power spectrum, the weak lensing signal, the distribution of galaxies. And then those predictions began to be checked at very high precision by surveys designed precisely to test them. And some of the predictions are not quite matching the data. The Hubble tension, the S8 tension, the early galaxy anomalies revealed by Webb. These are not all the same magnitude. They are not all equally firmly established. Some could still resolve as systematic errors are better understood. But the pattern of multiple tensions simultaneously, growing rather than shrinking with improved data, accumulating across independent measurements with different systematics, this pattern is what is making cosmologists take seriously the possibility that Lambda CDM is incomplete. Lambda CDM has been extraordinarily successful. It predicts the CMB power spectrum with remarkable precision. It predicts the large-scale distribution of galaxies. It predicts the abundances of light elements from Big Bang nucleosynthesis. It predicted the accelerated expansion, later confirmed by Type 1a supernovae. It has passed dozens of independent tests. This is precisely why the tensions are taken seriously. Not because the model is obviously wrong, it is not, but because a model this successful, encountering discrepancies at the 5 sigma level with some of its most basic predictions, the current expansion rate, is not the kind of model that is usually explained away by systematic errors. Models that work as well as Lambda CDM do not usually fail that badly by accident. The serious possibility being entertained in the field is that Lambda CDM is correct as a description of the universe in the regime it was designed for, but is incomplete, missing physics that matters at certain epochs or certain scales, and that the precision of current observations is now probing. This is how physics has worked before. Newtonian gravity worked extraordinarily well for centuries until measurements became precise enough and extreme enough to reveal its incompleteness at high velocities and strong gravitational fields. General relativity emerged not by discarding Newtonian gravity, but by embedding it in a larger framework that reduces to Newton's equations in the appropriate limit. The cosmological situation may be analogous. Lambda CDM may be the appropriate limit of some more complete theory that predicts new effects at early times or at specific scales that the complete theory would account for, but that Lambda CDM does not include. What that more complete theory is, nobody knows. But the data that Webb is generating, combined with the precision measurements of the CMB from Planck, combined with the growing library of gravitational wave standard sirens, combined with the galaxy surveys measuring large-scale structure. This convergence of extraordinarily precise data from multiple independent directions is creating the observational pressure that drives theoretical progress. We may be at the beginning of a revolution in cosmology, or we may be at the beginning of a long period of increasingly refined measurements, eventually revealing a mundane, systematic error. We do not know which. And that uncertainty, that genuine scientific openness, is itself one of the most honest things that can be said about the current state of our understanding of the universe. Let us now talk about what is coming, about the next generation of instruments and surveys that will either resolve the current tensions or deepen them. The Vera C. Rubin Observatory in Chile, now completing commissioning, will conduct the Legacy Survey of Space and Time. Over 10 years, it will photograph the southern sky repeatedly, building up a dataset of unprecedented breadth for studying the large-scale structure of the universe, weak gravitational lensing, the properties of dark energy, and the distribution of matter. Its measurements of S8 and other large-scale structure parameters will either confirm or challenge the tension with Planck's predictions. The Euclid satellite, launched in 2023 by the European Space Agency, is currently mapping the distribution of galaxies across a significant fraction of the sky, measuring their shapes and positions with the precision needed to constrain dark energy and matter clustering. Euclid's measurements of S8 and the growth rate of cosmic structure will provide independent constraints on the same tensions Planck and local surveys have identified. The Nancy Grace Roman Space Telescope, formerly WFIRST, planned for launch in the late 2020s, will conduct wide-field infrared surveys with Webb-like sensitivity over much larger areas of sky. Its measurements of Type 1a supernovae out to high redshifts and its weak lensing surveys will provide new constraints on the expansion history and matter distribution. The Simons Observatory and CMB-S4, ground-based CMB experiments, will measure the CMB temperature and polarization with higher resolution and sensitivity than Planck, providing refined measurements of the CMB parameters and potentially detecting new physics through measurements of CMB lensing and the kinetic Sunyaev-Zeldovich effect. Each of these surveys will generate data that directly bears on the Hubble tension and the S8 tension. The expectation is not that one of them will definitively resolve everything. Science does not usually work that way, but collectively, over the next decade, they will constrain the possible space of solutions dramatically. If the Hubble tension is a systematic error in the distance ladder, Euclid's independent measurement of H0 from baryon acoustic oscillations should converge towards 67. If it remains at 73, the tension persists. If the S8 tension is a problem with weak lensing measurements, Rubin's higher quality lensing data should bring it into agreement with Planck. If it remains discrepant, the tension is confirmed. If early dark energy is the solution to the Hubble tension, Euclid should see specific signatures in the galaxy power spectrum at scales sensitive to the sound horizon. If those signatures are not there, early dark energy is constrained out. The next decade in cosmology will be extraordinarily data-rich. The questions being asked now will be answered, definitively, one way or another, by data that either exists now in Webb's archives or will exist within a few years. This is the specific character of the current moment in cosmology. Not a vague unease about the standard model, not philosophical speculation about the nature of dark energy. A concrete, measured, quantified discrepancy at 5 sigma, confirmed by the most precise instrument ever built for the relevant measurements, with specific theoretical proposals under active investigation, and with multiple planned experiments that will directly test those proposals within a decade. This is what a potential revolution in physics looks like from the inside. Not dramatic, not sudden. A number that does not match another number, measured more and more carefully, resisting every attempt to explain it away, growing more significant with each new instrument, until the accumulated weight of evidence forces a change in the theoretical framework that accommodates it. Newton's gravity was not overturned overnight. The anomaly in Mercury's orbit was known for decades before Einstein's general relativity explained it.
The ultraviolet catastrophe, the failure of classical physics to correctly predict the spectrum of black-body radiation, was a known problem for years before Planck's quantum hypothesis and eventually quantum mechanics resolved it. The Hubble tension may be the current era's Mercury precession. A number that does not fit. A number confirmed by better and better instruments. A number pointing to something outside the current theoretical framework. What that something is, we do not know. But James Webb Space Telescope is making the evidence harder to ignore. Let us talk about what specifically Adam Rees and other Nobel laureates have said publicly about the Hubble tension. Because the way leading scientists are describing this situation has shifted noticeably over the past several years, and the shift in language is itself informative. In 2019, Rees wrote in Nature Astronomy a paper whose title included the phrase, "The tension has grown to a level of concern." This was measured, careful, scientific language. It was not claiming a discovery of new physics. It was acknowledging that the discrepancy was becoming hard to dismiss. By 2021 and 2022, the language had evolved. In public talks and interviews, Rees began using phrases like, "The tension is not going away," and "This is telling us something real." The framing shifted from "there might be a systematic error" to "the systematic errors we know about are not large enough to explain this." After the Webb results confirming the distance ladder in 2023, the language shifted further. Rees gave talks with titles including references to the possibility of new physics. He described the situation as one where the standard model may need to be revised. He stopped hedging about whether the Hubble tension was real and started asking what physics could explain it. This progression from might be a systematic error to probably not a systematic error to Webb says it's not a crowding bias represents the accumulation of evidence that has moved the scientific community from watching an anomaly to taking it seriously as a potential sign of new physics. Other Nobel laureates have weighed in. Saul Perlmutter, who shared the 2011 Nobel Prize with Rees and Brian Schmidt for the discovery of accelerating cosmic expansion, has publicly discussed the Hubble tension in the context of questions about the nature of dark energy. If the expansion rate today is higher than the early universe measurements predict, this could be telling us something about how dark energy evolves over cosmic time. John Mather, who shared the 2006 Nobel Prize for the discovery of the black-body spectrum and anisotropy of the CMB, has discussed the implications of Webb's early galaxy findings for our understanding of galaxy formation and the standard cosmological model. The common thread in what these scientists say publicly is a combination of caution and genuine surprise. Caution because the history of cosmology contains numerous cases where apparent discrepancies turned out to be systematic errors. Genuine surprise because the discrepancies are persisting and growing despite increasingly precise measurements designed specifically to resolve them. This is the scientific culture at its most honest, not claiming a revolution prematurely, not dismissing anomalies that are becoming increasingly hard to dismiss, holding the tension between these two impulses, skepticism and openness, while the data accumulates. Let us now talk about a specific aspect of Webb's observations that has not received as much popular attention as the Hubble tension or the early galaxy anomalies. What Webb has revealed about the intergalactic medium in the epoch of reionization. The epoch of reionization is the period when the universe transitioned from being filled with neutral hydrogen, which absorbs ultraviolet light and makes the universe opaque to it,
to being filled with ionized hydrogen, which is transparent. This transition was driven by the ultraviolet radiation from the first stars and galaxies, which ionized the surrounding intergalactic hydrogen. Precisely when reionization occurred, how long it lasted, and what kinds of sources drove it, whether predominantly young massive stars in ordinary galaxies or active galactic nuclei, or some combination, are questions that probe the earliest phases of cosmic structure formation. Webb spectroscopy of high redshift galaxies is providing new constraints on the timing and patchiness of reionization in ways that were not possible with previous telescopes. Specifically, Webb spectra of high redshift galaxies show the Lyman alpha emission line, a specific wavelength of ultraviolet light emitted by hydrogen atoms, with a range of properties that encode the ionization state of the intergalactic medium between us and the galaxy. When the intergalactic medium is neutral, before reionization, it absorbs Lyman alpha emission from background galaxies, suppressing the line. When it is ionized, after reionization, Lyman alpha can escape. By measuring how Lyman alpha emission varies across galaxies at different redshifts in the Webb data, astronomers can map how the reionization process progressed, identifying ionized bubbles around early galaxies, tracking the neutral fraction of the intergalactic medium as a function of redshift, and determining which types of galaxies were the main drivers of ionization. The Webb results suggest that reionization was a more complex and inhomogeneous process than previously modelled. The ionized bubbles around early galaxies appear to be larger and more developed at earlier times than some models predicted. The contribution of active galactic nuclei, growing black holes, to reionization may be larger than previously thought. This matters for our understanding of the early galaxy anomalies. If active galactic nuclei, which require massive central black holes, were significant contributors to reionization at redshifts of 6 to 8, this implies that supermassive black holes were already abundant and active at these early times, which connects back to the puzzle of how black holes grew so massive so quickly. The observations are pointing in a consistent direction. More structure, more massive objects, more organized activity in the early universe than the standard model comfortably accommodates. Let us talk now about one of the most technically challenging but potentially most informative things Webb is doing: measuring the chemical abundances of early galaxies through spectroscopy. The standard picture of cosmic chemical evolution holds that the early universe started with hydrogen and helium and trace amounts of lithium produced in Big Bang nucleosynthesis. All heavier elements, carbon, oxygen, nitrogen, iron, everything else on the periodic table heavier than lithium, were produced in stars and dispersed into the interstellar medium by stellar winds, planetary nebulae, and supernova explosions. The universe becomes progressively more chemically enriched over time as successive generations of stars live and die. This means that the very earliest galaxies should be chemically pristine, composed almost entirely of hydrogen and helium, with negligible amounts of heavier elements. As we look at progressively later epochs, the metallicity, the abundance of elements heavier than helium, should increase. Webb can measure the metallicity of high redshift galaxies through emission line spectroscopy. Emission lines from ionized oxygen, nitrogen, sulfur, and other elements trace the chemical abundances of the gas in these galaxies. What Webb is finding is broadly consistent with progressive chemical enrichment. Early galaxies are indeed less metal-rich than later ones. But the rate of chemical enrichment in some early galaxies appears faster than models predict. Some galaxies at redshifts of 4 to 6, the universe at 1 to 1.5 billion years, show metal abundances that standard models suggest should take longer to build up. This is connected to the more general theme of early galaxies being more evolved, more structured, more chemically enriched than expected at their cosmic epoch.
The chemical enrichment anomaly is another facet of the same underlying problem. Star formation in the early universe appears to have been more efficient and faster than our models suggest. Let us talk about the specific observational technique that makes Webb's chemical measurements possible, and why previous telescopes could not do this. The key is infrared spectroscopy. For galaxies at high redshifts above about 3, the optical emission lines that astronomers use to measure chemical abundances are redshifted into the infrared. The hydrogen Balmer lines, the oxygen forbidden lines at 3727 and 5007 angstroms, the nitrogen line at 6583 angstroms, all of these are shifted to wavelengths of 1 to several microns for galaxies at redshifts of 4 to 10. Hubble Space Telescope can observe into the near-infrared, out to about 1.7 microns, but its sensitivity drops off rapidly in this range, and its spectroscopic capabilities in the infrared are limited. Ground-based infrared spectroscopy is hampered by the thermal emission of the atmosphere and telescope, and by the strong absorption bands of water vapor in the atmosphere. Webb operates at cryogenic temperatures in space. Its mirrors and instruments are cooled to approximately 50 Kelvin, eliminating the thermal background that limits ground-based infrared observations. Its infrared spectrographs, NIR-SPEC and MIRI, can efficiently observe wavelengths from 0.6 to 28 microns. This range covers the redshifted optical emission lines of galaxies from redshifts of 1 all the way to beyond 20. This is a qualitative improvement, not an incremental one. With previous facilities, measuring the chemical abundances of a galaxy at redshift 6 required either very long integration times on the best ground-based spectrographs with substantial atmospheric limitations, or heroic observing programs with Hubble that were practical only for a handful of exceptional objects. With Webb, this kind of measurement is routine. Thousands of galaxies can be observed spectroscopically in a single pointing with NIR-SPEC's multi-object spectroscopy capability, obtaining simultaneous spectra of hundreds of galaxies in a single observation. This multiplexing capability is one of Webb's most transformative features for high redshift galaxy science. Instead of characterizing individual exceptional objects, Webb is characterizing populations, the statistical properties of thousands of galaxies at early cosmic times. This population-level characterization is what allows the anomalies to be recognized as real statistical trends rather than individual unusual objects. Let us talk about an important result that has come from Webb's ability to do this kind of statistical spectroscopy at scale: the discovery of what some researchers have called an overabundance of UV-bright galaxies in the early universe. One of the most basic things you can measure about a galaxy is how much ultraviolet light it emits, its ultraviolet luminosity. This traces the rate at which massive young stars are forming, since massive stars emit most of their energy in the ultraviolet. The ultraviolet luminosity function, the number of galaxies per unit volume as a function of ultraviolet luminosity, is a fundamental observable that tells you about the star formation activity in the universe. Standard models of galaxy formation make specific predictions for the ultraviolet luminosity function at different redshifts. These predictions are based on simulations of structure formation in the standard lambda-CDM framework: how dark matter halos grow, how gas falls into them, how efficiently stars form from that gas, how feedback from massive stars and active galactic nuclei regulates star formation. Webb has now measured the ultraviolet luminosity function at redshifts from 8 to 13, the universe at 300 to 600 million years old. with statistics vastly superior to any previous measurement. The result? There are more UV bright galaxies at these redshifts than the standard models predict. Specifically, at the bright end of the luminosity function, the most UV luminous galaxies, the excess is significant. There appear to be roughly 10 to 100 times more galaxies at the bright end at these redshifts than the standard models predict. This is a large discrepancy, not a 10% difference, a factor of 10 to 100 at the bright end. Several explanations have been proposed. One is that the stellar initial mass function, the distribution of stellar masses when a burst of star formation occurs, was different in the early universe, with more massive, more luminous stars per unit of gas converted to stars. More massive stars emit more UV photons per unit mass, which would make early galaxies brighter in the UV without requiring more total stellar mass. Another explanation is that feedback from supernovae and stellar winds was less efficient in early galaxies, that the violent processes that normally regulate star formation and keep galaxies from converting all their gas to stars quickly were less effective in the early universe, allowing brief episodes of extremely rapid star formation. A third explanation involves the role of active galactic nuclei. If some of the UV emission attributed to star formation actually comes from active black hole accretion, then the inferred star formation rates would be overestimates. But the problem of explaining the bright UV sources would shift to the problem of explaining why there are so many active black holes at early times. None of these explanations is fully satisfying on its own. Each requires some adjustment to the standard picture. Some require changes to poorly constrained parameters that have freedom in current models. Some require more radical departures. The bright end excess in the UV luminosity function is one of the most robustly established Webb results, measured independently by multiple teams using different galaxy samples and different analysis techniques, and it has not been explained away. Let us talk about something that connects the observational results we have been discussing to a deeper theoretical question about the nature of dark matter itself. The standard cosmological model assumes that dark matter is cold, that the dark matter particles were moving slowly compared to the speed of light when structure began to form. This cold dark matter forms the gravitational backbone of cosmic structure. Small fluctuations in the early universe grow under gravity to form dark matter halos within which galaxies form. The largest halos form from the bottom up, small halos merging to form large ones over billions of years. This cold dark matter framework has been extremely successful on large scales. It correctly predicts the distribution of galaxy clusters, the large-scale pattern of cosmic filaments and voids, the baryon acoustic oscillation scale, and many other observables. But on small scales, within individual galaxy halos, and potentially at the earliest epochs of structure formation, cold dark matter faces challenges. The missing satellite problem. Standard cold dark matter predicts more small dwarf galaxy satellites around the Milky Way than are observed. The too big to fail problem. The largest dark matter subhalos in simulations should host luminous galaxies, but some do not appear to. The core cusp problem. Cold dark matter predicts density profiles that rise steeply towards the center of halos, while observations of some galaxies suggest shallower central profiles. These small-scale challenges have long been known and are sometimes attributed to baryonic physics, to the effects of star formation, supernova feedback, and other processes that simulations may not model perfectly, rather than to problems with the nature of dark matter itself. But Webb's observations add a new dimension. If early galaxies formed faster and more efficiently than cold dark matter models predict, if more massive halos were in place at earlier times than expected, this could point to a modification in the dark matter particle physics
rather than just baryonic effects. Warm dark matter, where dark matter particles were moving at significant fractions of the speed of light when structure formed, suppressing the growth of small halos, was previously considered as a possibility, but constrained by observations of the Lyman alpha forest and other probes of small-scale structure. Some forms of warm dark matter are disfavored. Fuzzy dark matter, or ultralight axion dark matter, is a more exotic proposal in which dark matter consists of extremely light particles with a de Broglie wavelength comparable to the sizes of dwarf galaxies. This would suppress structure on small scales through quantum interference effects while preserving large-scale structure. It could potentially explain some small-scale challenges while making specific predictions for the properties of the earliest structures. Interacting dark matter, proposals in which dark matter particles have significant self-interactions, can alter the internal structure of dark matter halos and potentially affect how quickly structure forms. None of these alternatives has become a leading candidate. Cold dark matter remains the standard assumption, but the accumulation of tensions on small scales from galaxy observations, on early universe scales from Webb's observations, is broadening the space of dark matter models being seriously considered. Let us now talk about a specific challenge to standard cosmology that Webb has raised in a completely unexpected context: the discovery of what appear to be very old stellar populations in early galaxies. When you observe a galaxy, its light is a mixture of light from all the stars it contains. By modelling this mixture, fitting the spectral energy distribution, the distribution of light across different wavelengths, you can estimate the ages and masses of the stellar populations present. This technique is called stellar population synthesis. Applied to early galaxies observed by Webb, this technique has revealed something surprising. Some early galaxies appear to contain stellar populations that are significantly older than you would expect given the age of the universe at the redshift where they are observed. Specifically, some galaxies at redshifts of 4 to 6, when the universe is 1 to 1.4 billion years old, appear to contain stars that formed 500 million to 1 billion years before the epoch of observation. This means stars forming at redshifts of 10 to 15, when the universe was only 200 to 400 million years old, implying that star formation began at extraordinary rates at very early times, built up a population of old stars, and those stars are now being observed indirectly through their contribution to the spectral energy distributions of the galaxies containing them. This is distinct from directly observing the high redshift galaxies themselves. It is an indirect inference, reading the archaeological record of past star formation from the present properties of lower redshift galaxies. The inference depends on stellar population synthesis models that have their own uncertainties. But the pattern, early and efficient star formation, producing old stellar populations that are visible archaeologically in later epoch galaxies, is consistent with the direct observations of bright, massive, early galaxies at high redshifts. It is another line of evidence pointing in the same direction. The universe's star formation history, the rate of star formation per unit volume per unit time across cosmic history, had a well-established shape before Webb. It rose from the Big Bang, peaked around redshift 2 to 3, approximately 2 to 3 billion years after the Big Bang, and declined to the present day. Webb's observations suggest that the very early portion of this history, the rise from the Big Bang to the peak, may have been steeper and earlier than previously thought. More stars forming more quickly, earlier in cosmic history. Let us talk now about what a resolution of these tensions would actually look like. What kind of new physics or new observations
would constitute a satisfying answer to the questions Webb has raised. The most intellectually satisfying resolution would be a single modification to the Standard Model that simultaneously explains all the tensions: the Hubble tension, the S8 tension, the early galaxy abundances, the early massive black holes, the UV luminosity function excess, the chemical enrichment rates. A single new ingredient that, when added to lambda CDM, brings predictions into agreement with all observations. No such unified resolution has been found. This absence is itself informative. It suggests that either the tensions will resolve separately, each with its own mundane explanation that has not yet been identified, or that the new physics required is more complex than a single simple addition to the Standard Model. The history of successful revisions to physical theories suggests that when a model is genuinely incomplete, the resolution often involves a conceptual shift that restructures how we think about the problem, rather than simply adding a term to an equation. General relativity did not just add a correction to Newtonian gravity, it reconceived the nature of space, time, and gravity. Quantum mechanics did not just add corrections to classical mechanics, it introduced a fundamentally different description of physical reality at the atomic scale. If the standard cosmological model is genuinely incomplete, if there is new physics at early times or new physics in the dark sector, the resolution may require a conceptual shift of comparable depth. Not just a new particle, not just a modification to dark energy, but a different way of thinking about one or more of the foundational elements of cosmology. What those elements might be, nobody knows. Dark energy as a cosmological constant has no theoretical justification other than its observational success. The nature of dark matter is unknown beyond its gravitational effects. The initial conditions of the universe, the primordial power spectrum of density fluctuations, are observed but not explained by the Standard Model. Inflation, the proposed period of exponential expansion in the very early universe, is not uniquely predicted, but instead is a family of models, some of which are now being constrained by CMB polarization observations. Any of these could be modified. All of them are under theoretical scrutiny. The data from Webb and from the next generation of surveys will help determine which, if any, of these foundational elements requires revision. Let us now talk about one more specific thing Webb has found that has not yet been fully absorbed into the discussion of cosmological tensions: what it is revealing about the morphology and structure of early galaxies at a level of detail never previously possible. Before Webb, our knowledge of galaxy morphology, the shapes and structures of galaxies, was essentially confined to the universe at redshifts below about 3. Hubble could image galaxies with exquisite detail in the local and intermediate redshift universe. At redshifts above 3, galaxies appeared as small, faint blobs in Hubble images. You could detect them and measure their brightness, but detailed structural information was beyond reach. Webb has changed this. Its superior resolution in the near-infrared, combined with the fact that infrared wavelengths trace rest frame optical light for high redshift galaxies, which traces the bulk stellar population rather than just the brightest young stars, allows detailed structural analysis of galaxies at redshifts of 4, 6, 8, and beyond. What is being found is striking. Disk galaxies, the flat, rotationally supported structures exemplified by our own Milky Way, appear to be present at redshifts of 4 to 6 in surprising numbers. In the Standard Model, disk galaxies are expected to be fragile, easily disrupted by the frequent mergers expected in the early universe when structure formation was vigorous and mergers were common.
The expectation was that the early universe would be dominated by irregular, merger-disturbed morphologies, with organized disk structure emerging only at later times as the merger rate declined. Webb is finding organized disks, with visible spiral arms in some cases, at redshifts where they should not be common. This is another facet of the general pattern. More organized, more structurally mature galaxies in the early universe than expected. The presence of organized disks in the early universe places constraints on the frequency and violence of mergers at early times. Disks are disrupted by major mergers. If disks are present, major mergers cannot have been so common as to constantly destroy them. This could point to modifications in the merger rate, which depends on the structure of dark matter halos, or to the ability of disks to reform quickly after mergers, or to a suppression of major mergers in the early universe relative to what cold dark matter models predict. The morphological results from Webb are still being analysed and interpreted. The full implications for galaxy formation theory are being worked out. But the consistent pattern is that the high redshift universe seen by Webb is more structured, more organised, more chemically enriched, and more massive than the standard model comfortably accommodates. This is what Nobel Prize winners mean when they say we might be looking at a different universe. Not literally different, the same universe we live in, observed with better tools than we have ever had before. But a universe whose early history is not quite what our best model predicted. A universe that appears to have organised itself faster, formed stars more efficiently, grown its black holes more rapidly, and built its disk galaxies more quickly than the model that has been the foundation of cosmology for 20 years suggests. Something made these galaxies so quickly. Something is driving the universe to expand faster than the early universe measurements predict.
Something produced more structure, more mass, more chemistry, more organisation in the first billion years than our models said was possible. We do not know what that something is, but we are measuring its effects precisely with the most powerful space telescope ever built, in data that is accumulating every day, in papers appearing every week, in a scientific community that is beginning to acknowledge that the map may not be the territory. The universe has something to tell us that we have not yet learned to hear. Webb is the first instrument sensitive enough to begin hearing it. Let us talk about what the scientific community actually does when confronted with anomalies of this kind, about the sociology of cosmological crises, because it is instructive to understand how a mature, successful scientific field processes the possibility that its foundational model might be incomplete. The instinct in any scientific field when data conflicts with theory is first to look for errors. This is correct scientific practice. Before invoking new physics, before claiming a discovery of something outside the standard model, you must be confident that the measurement is right, that the instruments are calibrated correctly, that the analysis pipelines are sound, that the systematic errors are understood and bounded. In the case of the Hubble tension, this process has been extraordinarily thorough. The SHOES team has examined every step in their distance ladder. They have replaced Hubble Space Telescope observations with Webb observations to check for crowding bias. They have used multiple calibrators for the Cepheid period luminosity relation. They have checked their Type 1a supernova sample for selection effects. They have published their methodology in exhaustive detail, allowing independent teams to scrutinize and challenge every assumption. Independent groups using completely different methods, the H0LICOW and TDCOSMO collaborations using strong gravitational lensing time delays, the Chicago-Carnegie Hubble program using the tip of the red giant branch as a distance indicator, teams using megamasers in water maser galaxies have reached broadly consistent values around 70 to 74 kilometers per second per megaparsec,
all higher than the Planck value of 67. The Planck collaboration has similarly examined their analysis for errors. The CMB measurement is extraordinarily robust. It is not based on a chain of calibrations like the distance ladder, but on fundamental physics of sound waves in the early universe plasma. The inference of H0 from the CMB requires assuming the standard cosmological model, but given that model, the measurement is very precise. After years of this scrutiny, the consensus has shifted from probably a systematic error somewhere to we cannot find the systematic error despite looking very hard. This shift is what has moved the conversation from measurement troubleshooting to theoretical investigation. The same process is underway for the early galaxy anomalies. When the first Webb photometric candidates for massive early galaxies appeared in 2022, the immediate skeptical response was, photometric redshifts can be wrong. This was correct and reasonable. Photometric redshifts estimated from broadband colors are not reliable enough to claim a discovery on their own. The response of the scientific community was not to declare a crisis. It was to obtain spectroscopic confirmation. This has now been done for numerous objects. The spectroscopic redshifts confirm the photometric estimates. The objects are real. They are at the claimed redshifts. Their properties, the brightness, the inferred masses, the chemical abundances, are measured from spectra that do not depend on model-dependent photometric estimates. This is how science is supposed to work. Skepticism maintained until evidence accumulates to a level that is difficult to attribute to error. Then revision of the theoretical framework rather than denial of the evidence. The cosmological community is now in the transition zone, past the stage of easily dismissed anomalies, but before the stage where new theory has settled. This is an uncomfortable place to be. It is also where the most important scientific work happens. Let us talk about a specific theoretical framework that has received renewed attention as a result of the Webb anomalies. The possibility that the primordial power spectrum of density fluctuations is different from what the simplest inflationary models predict. The primordial power spectrum is the distribution of density fluctuations in the very early universe, the tiny overdensities and underdensities that later grew under gravity to become galaxies, galaxy clusters, and cosmic voids. In the standard inflationary model, this spectrum is nearly scale invariant. Density fluctuations have approximately the same amplitude across all size scales, with a slight tilt toward larger fluctuations on large scales. This nearly scale invariant spectrum is one of the key predictions of inflation. It is confirmed by CMB observations to high precision. The measured spectral index, n sub s, is approximately 0.965, close to, but slightly less than, the pure scale invariant value of 1. But nearly scale invariant leaves room for features. The primordial power spectrum could have bumps, enhanced power at certain scales, that would produce more structure at those scales and thereby more rapid halo formation and more efficient galaxy assembly at early times. If the primordial power spectrum has enhanced power on small scales, scales corresponding to the masses of the early galaxies Webb is observing, this could explain why more massive structures are in place at earlier times than the standard spectrum predicts. More power on small scales means more dark matter halos of the relevant masses at earlier times, meaning more places for galaxies to form and more gas available for rapid star formation. This kind of non-standard primordial power spectrum could arise from specific inflation models, particularly models with features in the inflaton potential, the hypothetical field that drove inflation. If the inflaton potential has a local feature, a bump, a step, a sudden change in slope, at a specific location, this imprints a corresponding feature on the primordial power spectrum at the scale that exits the Hubble horizon at that moment during inflation.
The CMB constrains the primordial power spectrum on large scales, the largest observable cosmic scales, with high precision. But the CMB has limited power to constrain the spectrum on the small scales corresponding to the masses of early galaxies. These scales are below the CMB resolution limit. This means there is observational room for enhanced small-scale power without conflicting with CMB constraints. Webb's observations of early galaxies are probing scales of the power spectrum that are not yet well constrained by other observations. If this explanation is correct, if the primordial power spectrum has enhanced small-scale power from inflationary features, this would represent genuinely new physics in the inflationary era. It would not be a modification to post-inflationary physics, but to the earliest moments of the universe's history. This proposal is speculative. It is not yet tested against the full range of observations that would need to be consistent. But it illustrates the kind of theoretical thinking being generated by Webb's anomalies, reaching back to the earliest moments of cosmic history to find the physics that could produce what is being observed. Let us talk about the specific numbers from the Webb early galaxy observations that put the tension with standard models in sharpest relief. The standard model of galaxy formation, embodied in hydrodynamical simulations like Illustris TNG, Eagle, Simba, and others, makes specific predictions for what the most massive galaxies should look like at different redshifts. These simulations solve the equations of gravity, gas dynamics, star formation, and feedback self-consistently in volumes large enough to contain statistically significant numbers of massive galaxies. At redshift 10, the universe at about 480 million years old, the most massive galaxies in Illustris TNG simulations have stellar masses of roughly 10 to the power of 9 to 10 to the power of 10 solar masses, a few billion to 10 billion solar masses at most. These are the most extreme objects the simulation produces, representing the rare peaks of the density distribution. Webb observations of galaxies at redshift 10 have found objects with inferred stellar masses approaching 10 to the 10th power to 10 to the 11th power solar masses, 10 billion to 100 billion solar masses in early analyses. If these masses are correct, they exceed what the standard simulations produce by a factor of 10 to 100 at the extreme end. These mass estimates carry significant uncertainties. Stellar mass estimates from photometry depend on assumed stellar populations, dust properties, and star formation histories. The uncertainties can be factors of a few in either direction for individual objects. It would be incorrect to treat these numbers as precise. But the excess is not concentrated in a single outlier. It appears in the statistical tail of the galaxy mass function, in the number density of the most massive objects, and the excess persists across multiple independent analyses using different photometric data and different population synthesis codes. The systematic errors in stellar mass estimation would have to be consistently biased in the same direction across all methods and all teams to explain the full excess. This is possible, but increasingly strained as an explanation. Another way to quantify the tension uses the concept of baryon fraction, the fraction of the total mass in a dark matter halo that is in the form of stars. In standard galaxy formation theory, this fraction is limited by the efficiency of star formation and by feedback processes. Even in the most efficient scenarios, the stellar mass is at most a few % of the total halo mass, and typically much less. For some early massive galaxy candidates in Webb data, the implied baryon conversion efficiency, the fraction of all baryons in the halo that have been converted to stars, approaches or exceeds what standard feedback models allow. In some extreme cases, the implied efficiency approaches 100%, as if essentially all the baryons in the halo had been converted to stars,
with no loss to outflows or feedback. Standard galaxy formation models produce maximum conversion efficiencies of perhaps 20 to 30% in the most extreme cases. Reaching 50 to 100% efficiency would require either the near-complete suppression of feedback, which is responsible for regulating star formation, or some process that concentrates gas more efficiently than standard models predict. These extreme cases are not the typical high redshift galaxy. They are the tail of the distribution.
But the existence of a tail that reaches implausible efficiencies is itself a problem for the Standard Model, because the Standard Model's predictions for the most massive objects at any epoch are the most robust. They are the least sensitive to uncertain feedback physics and the most directly determined by the growth rate of dark matter structure. Let us talk about what is known as the impossibly early galaxy problem, a phrase that began appearing in the scientific literature in 2022 and 2023, and why this language, unusual for scientific papers, appeared. Scientists are generally conservative with language. Journals resist overstated conclusions. Referees push back on dramatic phrasing. When a paper title or abstract uses language like impossible or challenges the standard model or requires new physics, the author has typically made a careful judgment that the language is justified by the strength of the evidence. The phrase impossibly early galaxies appeared because several teams independently reached the conclusion that the stellar masses they were measuring, if confirmed spectroscopically, were inconsistent with the Standard Model, not in a quantitative sense, but in an absolute sense. Not harder to explain than we expected, but cannot be produced by the Standard Model even in its most optimistic configurations. This is a strong claim. It requires that the maximum efficiency of star formation in the most favourable dark matter halos at the earliest times is insufficient to produce what Webb is observing. It requires that the Standard Model not just underpredict the observations, but be categorically unable to accommodate them. Subsequent spectroscopic confirmation of some of these objects has both validated that they are at the claimed redshifts and partly moderated the mass estimates. Spectroscopic data constrains stellar populations more precisely than photometry, and some early mass estimates based on photometry have been revised somewhat downward. The impossible language has been tempered. But the underlying issue has not gone away. The spectroscopically confirmed early galaxies remain more massive, more structured, and more chemically enriched than standard models prefer. The impossibility has moderated into a significant tension. The tension has not resolved. Let us talk now about the role of Webb in observing another aspect of the early universe that connects to the cosmological tensions, the cosmic dawn, the epoch of the very first stars. The first stars are called population 3 stars, named in the classification scheme where population 1 stars like the Sun are metal-rich, population 2 stars like those in globular clusters are metal-poor, and population 3 stars are the hypothetical first generation formed from chemically pristine primordial gas, containing only hydrogen, helium, and trace lithium. Population 3 stars have never been directly observed. They are expected to have formed in the first few 100 million years after the Big Bang and to have lived very short lives, massive and luminous, exploding as supernovae after only a few million years, enriching the surrounding gas with the first heavy elements. Their deaths ended the era of pristine star formation and began the process of chemical enrichment that eventually produced the metal-rich environments in which planets and potentially life form. Detecting population 3 stars directly is one of Webb's most ambitious scientific goals. The challenge is that they are expected to be at very high redshifts, the universe at less than 300 million years old, making them extraordinarily faint.
Furthermore, they are short-lived, so the window in which they can be observed is narrow. Webb has not yet definitively detected population 3 stars directly, but it has found intriguing hints. In 2023, a team reported detecting in a Webb spectrum of a galaxy cluster a highly magnified background galaxy at very high redshift that shows emission line ratios suggesting the presence of population 3 stars. The interpretation is controversial. Other explanations for the observed emission lines are possible, but the observation is being taken seriously as a possible first glimpse of the very first stellar generation.
More significant for the purposes of this discussion is what Webb is learning about the transition from population 3 to population 2 star formation, the era when the first chemical enrichment occurred and when the first galaxies were building their stellar populations. The chemical signatures in high redshift galaxy spectra observed by Webb, the abundance patterns of carbon, oxygen, nitrogen and other elements, carry information about what kinds of stars produced those elements. Massive stars produce different abundance patterns than low-mass stars. Very massive population 3 stars produce specific nucleosynthetic signatures that should be visible as peculiar abundance ratios in the earliest chemically enriched gas. Some Webb spectra of very high redshift galaxies show abundance patterns that are unusual, different from what is seen in lower redshift galaxies and potentially consistent with enrichment by a population 3 generation.
This is not yet a firm detection. The uncertainties are large, but it is a direction of active investigation. If population 3 stars are eventually detected directly or characterized indirectly through their chemical signatures, this would provide a completely new constraint on the physics of the very first cosmic structures, and potentially illuminate the question of why early galaxies formed as efficiently as Webb suggests they did. Let us now talk about something that has emerged as an unexpected finding from Webb, what it is revealing about galaxies in the local and intermediate redshift universe, not just the early universe. Webb was designed with the early universe as a primary science goal, but because it is so sensitive and has such broad wavelength coverage, it is also transforming our understanding of galaxies at lower redshifts, the universe at redshifts of 1 to 3, when the universe was 2 to 6 billion years old. In particular, Webb's infrared sensitivity is revealing the dust-obscured component of star formation and black hole activity in these intermediate redshift galaxies with unprecedented clarity. Dust absorbs ultraviolet and optical light and re-emits it in the infrared. In heavily star-forming galaxies, much of the star formation is obscured by dust and therefore invisible in optical surveys. Webb's infrared coverage reveals this hidden component. What is being found is that the dust-obscured component of cosmic star formation history may be larger than previously estimated, that surveys relying on ultraviolet and optical observations systematically underestimate the total star formation rate because they miss the dust-obscured portion. This has implications for the total stellar mass buildup history of the universe. If more stars formed in dusty environments that were invisible to previous surveys, the total stellar mass at any epoch may be higher than census-based estimates suggested. This is relevant to the early galaxy anomalies because it potentially changes the baseline against which early galaxies are being compared. If the total amount of star formation was systematically underestimated at intermediate redshifts, models calibrated to reproduce the observed star formation history may be systematically off in ways that affect their predictions for the early universe. This is not a resolution of the early galaxy problem. The anomalies seen at redshifts above 8 are not a consequence of dust-obscured star formation at redshift 2. But it illustrates that Webb is not just discovering new things about the early universe. It is revising our understanding of the entire history of cosmic star formation in ways that interact with and complicate the interpretation of the highest redshift anomalies. Let us talk about one specific discovery that Webb has made, which is not directly related to the Hubble tension or the early galaxy problem, but which has captured significant scientific attention: the detection of carbon dioxide in the atmosphere of an exoplanet, and what this demonstrates about Webb's capabilities for chemistry. In 2022, Webb detected carbon dioxide in the atmosphere of the exoplanet WASP-39b, a gas giant orbiting a star about 700 light-years away. This was the first clear detection of CO2 in the atmosphere of an exoplanet. This is relevant to the broader story, not because CO2 in the atmosphere of a hot gas giant is significant for the search for life. It is not. But because it demonstrates what Webb can do with spectroscopy of planetary atmospheres. The technique is the same one being used to measure chemical abundances in distant galaxies, spectroscopy revealing the fingerprints of specific molecules and atoms in the light passing through or emitted by an atmosphere. Webb's sensitivity and wavelength range make it capable of detecting atmospheric signatures in the atmospheres of potentially habitable rocky exoplanets. Not today, because current observations of rocky planets in the habitable zones of their host stars are still at the frontier of what is possible, but in principle with sufficiently long observations of the right targets. This connects the cosmological science Webb is doing, measuring the universe's expansion rate, characterizing early galaxies, probing the epoch of reionization, to what is arguably the most profound question Webb can potentially address in the longer term: whether the atmospheres of Earth-like planets around nearby stars show signs of life. These are very different science cases using the same instrument, but they share a common feature. Webb is operating in a regime of sensitivity and spectroscopic capability that simply did not exist before. The cosmological anomalies it is revealing are a product of this new capability applied to the largest scales. The atmospheric chemistry it is measuring is the same capability applied to the smallest scales. Let us now talk about what is perhaps the deepest implication of the tensions we have been discussing, not just for cosmology, but for physics more broadly. The standard cosmological model, lambda-CDM, rests on three foundational pillars: general relativity as the theory of gravity on all scales, the standard model of particle physics as the theory of matter and energy, and inflation as the mechanism generating the initial conditions. Dark matter and dark energy are added as additional components required by observations, but not yet explained by fundamental theory. If the Hubble tension represents genuine new physics, it almost certainly lives in one of two places: either in the behavior of dark energy, something in how the vacuum energy or whatever is driving the acceleration evolves over cosmic time, or in some modification of the expansion history at early times, which could involve either a new component of energy or a modification to gravity at cosmological scales. If the early galaxy anomalies represent genuine new physics, it could live in the primordial power spectrum, a feature of inflation, or in the nature of dark matter on small scales, or in some physical process we have not yet identified that made star formation more efficient in the early universe. What is striking is that these potential new physics live in different sectors of the theory. The Hubble tension points toward dark energy or early universe modifications. The early galaxy anomalies point toward structure formation or star formation physics. These are different parts of the cosmological framework. This means either they have separate explanations, two different independent pieces of new physics, or they have a common origin in something more fundamental that affects the expansion history and structure formation simultaneously. A common origin would be more theoretically elegant and more physically satisfying. It would suggest a single new ingredient, possibly something in the dark sector, possibly a modification to inflation, possibly something in the physics of the very early universe, that simultaneously explains why the local expansion rate is high and why early galaxies formed so efficiently. Finding that common origin, if it exists, would represent one of the most significant theoretical advances in cosmology since the discovery of dark energy in 1998. It would be the beginning of physics beyond lambda CDM, in a sense that is both observationally motivated and theoretically coherent. This is what is at stake in the current data, not just adjusting a parameter here or adding a term there, potentially reconceiving the physics of the dark universe, dark matter, dark energy, inflation, in a way that makes new predictions, that connects previously unrelated phenomena, that illuminates why the universe we observe is structured the way it is. Webb is the instrument that has made the evidence for this possibility sharper than it has ever been. Every week its data archives grow. Every month new papers appear analysing those data. Every semester the picture becomes clearer, not resolving into something simple and familiar, but sharpening into something that looks genuinely new. We are living through the early stages of this process. We do not yet know how it ends. But the instruments are better than they have ever been. The data are accumulating. The tensions are real.
And the universe, it seems, has not finished surprising us. Let us talk about one more specific result that deserves attention before we go further. What Webb has found when looking at gravitational lenses, and why lensed observations are among the most powerful tools for probing early universe physics. Gravitational lensing occurs when a massive object, a galaxy cluster, a massive galaxy, lies between us and a more distant source. The gravitational field of the intervening mass bends the light from the background source, distorting and magnifying it. In extreme cases, multiple images of the same background object appear, or the background object is stretched into arcs or rings. For observing the early universe, gravitational lensing is transformative because it provides free magnification. A galaxy cluster, acting as a gravitational lens, can magnify background galaxies by factors of 10, 50, even 100 or more in exceptional cases. Objects that would otherwise be too faint to detect or too small to resolve become visible and analyzable. Webb's extraordinary sensitivity, combined with its infrared capability for observing high redshift sources, makes it uniquely powerful for lensed observations. Several of Webb's most scientifically significant early results have come from observations of galaxy clusters acting as gravitational telescopes. The cosmic cliffs image, one of Webb's first released science images, showed the edge of a star-forming nebula in extraordinary detail. But the galaxy cluster images, showing arcs and multiple images of lensed background galaxies, are where the deepest science is being extracted. Through lensing magnification, Webb has been able to study individual star-forming regions within galaxies at redshifts of 4 to 7, spatial resolution that would otherwise require a telescope larger than can currently be built. In some lensed galaxies, individual star clusters, groups of perhaps thousands to millions of stars, can be resolved and characterized. This is qualitatively different from the statistical measurements we discussed earlier. Instead of measuring the aggregate properties of whole galaxies, Webb can look inside individual early galaxies at the scale of star-forming regions. It can see where the stars are forming, how bright the individual clusters are, how they are distributed spatially. What is being found in these high-resolution lensed views is that early galaxies are not smooth, featureless blobs. They are structured on small scales, containing bright, compact star-forming clumps, in some cases distributed in disk-like arrangements, in others concentrated in central regions. The internal structure of early galaxies is complex and varied, more so than simplified models assumed. In 2022,
Webb observed through a gravitational lens a galaxy called the Sunrise Arc, one of the most highly magnified galaxies known, and resolved individual star clusters within it at a redshift of approximately 1. But the technique being applied to such objects at higher redshifts promises similar resolution at redshifts of 3, 4, 5, and beyond. In the Pandora's cluster observations, released in 2023, a region combining the lensing power of multiple galaxy clusters in the same field, Webb found numerous lensed background galaxies with sufficient magnification to begin structural analysis. Several of these are at redshifts above 6, the universe at less than 1 billion years old, and show complex internal structure that constrains the physics of early star formation. The lensing observations connect the statistical picture from surveys finding an excess of massive early galaxies to the physical picture, what is actually happening inside these galaxies at the level of individual star-forming regions. This connection is essential for building a complete understanding of why the early universe formed stars so efficiently. Let us talk about what is perhaps the most philosophically significant aspect of the current situation, about what it means for human knowledge that the most powerful instrument ever built for observing the universe is finding things that do not fit our best model of the universe. There is a temptation in popular science communication to frame scientific anomalies in one of two ways. Either they are exciting hints of revolutionary new physics, or they are likely to resolve as systematic errors that will be found and corrected. Both framings have some truth in different cases. Some anomalies are precursors to major discoveries. Others evaporate under scrutiny. What is unusual about the current situation in cosmology is the persistence and growth of the anomalies. The Hubble tension has been known in some form since the early 2000s and has grown in statistical significance with every improvement in measurement. The early galaxy anomalies appeared with Webb's first data and have been confirmed and extended with every subsequent semester of observations. In most historical cases, where a measurement anomaly was later explained as a systematic error, the anomaly diminished as measurement precision improved. Additional data revealed the source of the error. When an anomaly grows with increasing measurement precision, this is the pattern characteristic of a real physical signal rather than a systematic artifact. The Hubble tension is now at 5 sigma, higher than it was at 4 sigma, which was higher than it was at 3 sigma. It has grown consistently as the measurements have improved. Webb confirmed rather than explained away the distance ladder. This is the pattern of something real. The early galaxy anomalies went from photometric hints to spectroscopic confirmation to population-level statistics as Webb accumulated data. They have not evaporated, they have become more concrete. This pattern, growing in significance with improving data, confirmed rather than refuted by independent methods, is what makes the current situation in cosmology genuinely exciting and genuinely uncertain simultaneously. Exciting because real signals pointing to new physics look exactly like this. Uncertain because we cannot yet identify what the new physics is. This is the frontier of human knowledge about the universe, not the comfortable place where everything is understood and the textbooks are right. The uncomfortable place where the data is telling us something the theory does not yet know how to explain. This is where science lives at its most alive. Go outside tonight and look up. Find the darkest part of the sky. Let your eyes adapt. Then look at the faint smear of the Milky Way if it is visible, or simply look at the stars, at the darkness between them, at the depth that the eye cannot quite measure, but the mind knows is there. What you are looking at is a universe that is 13.8 billion years old. That is the number in the textbooks. That is what the standard model says. But something may be wrong with that number, or with the model that produces it. Here is what we know. The universe is expanding. Every galaxy beyond our local group is moving away from us. More distant galaxies move faster. The rate of this expansion, the Hubble constant, is one of the most fundamental numbers in cosmology. It tells us how fast the universe is growing, and from that, how old it is, how large the observable portion is, what its future holds. We have measured this number two ways. From the nearby universe, using chains of distance measurements reaching from our own galaxy to the most distant supernovae, the answer is approximately 73 kilometers per second per megaparsec. From the early universe, using the pattern of fluctuations in the oldest light in the cosmos, the cosmic microwave background, the answer is approximately 67. These two numbers do not agree. They are separated by 8%. At a statistical significance of 5 sigma, the threshold physicists use to claim a discovery. Not a fluctuation, not a rounding error, a genuine, reproducible, growing discrepancy between two precisely measured values of the same physical quantity. James Webb Space Telescope was supposed to resolve this. Its superior resolution and infrared capability was supposed to reveal the systematic error in the distance ladder, the crowding of stars in distant galaxies, the blending of light, the calibration offset that was making the local measurement come out too high. Webb looked, with greater precision than any previous instrument, at the same Cepheid stars in the same galaxies that previous measurements used. The systematic error was not there. The distance ladder is correct. The tension is real. And Webb found something else. When it looked at the earliest universe, at galaxies seen when the cosmos was only a few 100 million years old, it found objects that should not be there. Galaxies more massive than our models say could have formed so quickly. Black holes weighing billions of solar masses at a time when there was not enough time for them to grow to that size through standard processes. Disk galaxies with organized spiral structure appearing when the universe was barely organized enough to form stars. Chemical abundances suggesting generations of stellar evolution had already occurred when the universe was barely old enough for one generation to live and die. These are not marginal anomalies. They are not a single unusual object that might be a measurement error. They are populations, statistical excesses confirmed spectroscopically by multiple independent teams using multiple independent data sets. Something in the early universe formed faster than we thought, organized itself more efficiently, built more mass, more structure, more chemistry in less time than our best models. Models that have passed every previous test for 20 years, say was possible. We do not know what that something is. The Nobel laureates who built the foundation of modern cosmology are saying publicly that the universe may be telling us something we did not know, not as a figure of speech, as a precise scientific statement. The data does not fit the model, and the model may need to change. This happens rarely in physics. General relativity replaced Newtonian gravity, not because Newtonian gravity was wrong, but because it was incomplete. It worked everywhere we had tested it, and failed where we had not yet looked. Quantum mechanics replaced classical physics, not by discarding everything that came before, but by revealing the deeper structure underlying it. What Webb is revealing may be the same kind of thing. Lambda CDM, the standard cosmological model, works. It predicted the CMB fluctuations. It predicted the distribution of galaxies. It predicted accelerating expansion. It passes dozens of tests. And now, at the frontier of precision in the regime of the early universe, it is encountering data it did not predict. A 5 sigma discrepancy in the expansion rate. Galaxies too massive too soon. Black holes too large too early.
disks too organized too quickly. The universe is not reading the textbook. Look up tonight. The light coming into your eyes left those stars years, decades, centuries, billions of years ago. You are looking at the past. Some of that light left its source before Earth existed. Some left before the sun ignited. Some left from galaxies so distant and early that the universe was barely recognizable as the universe you live in. And somewhere in that light, in the patterns of what Webb is measuring, in the spectra of those early galaxies, in the precise value of how fast the space between us and those galaxies is growing, there is a message from the universe about its own nature that we have not yet fully decoded. The instruments are better than they have ever been. The data is accumulating every day. The tension is real. And the universe, it seems, has more to say than we have yet learned to hear.